Every textbook solar system diagram is a lie of convenience. It shows planets lined up flat, like beads on a wire, with the sun sitting in the middle. But that picture has no up, no down. So what is actually above the sun and what's below it? Almost nobody can answer that question because almost nobody was ever taught to ask it. That gap in your understanding isn't your fault. It's baked into how the solar system got drawn in the first place. So let's fix it properly. Start with the honest answer. In empty space, there is no universal up or down. Direction only means something relative to something else. So when we ask what's above the sun, we first need to agree on what above is measured against. Astronomers do have an answer. It's called the ecliptic plane, and it's the flat disk most of the planets roughly orbit within. That plane exists because the early solar system was a spinning disk of gas and dust, and everything condensed from it flat, like batter spreading in a pan. So, above the sun means north of that disk. Below means south of it. And here's the part your diagram never showed you. Almost every spacecraft humanity has ever launched stays inside that flat plane. We've sent probes past every planet. We've landed on Mars 6 times, but almost nothing has ever left the plane to look at the sun from above. Why not? Because leaving the plane is one of the most expensive maneuvers in orbital mechanics. A rocket launched from Earth already carries our planet's orbital momentum. That momentum points sideways, along the plane, not up toward the sun's pole. To go north, a spacecraft has to cancel out that sideways motion entirely. That takes an enormous amount of fuel. So for decades, no one built a mission that could afford it. The poles of our own sun stayed unseen. Then, in 1990, one mission solved the fuel problem with a trick borrowed from billiards, not brute force. It's called Ulysses, and it remains the only spacecraft ever to fly over the sun's poles. Ulysses couldn't carry enough fuel to bend its own path. So engineers sent it to Jupiter first and let Jupiter's gravity do the bending. Jupiter's gravity flung the probe up and out of the ecliptic onto a new path that finally crossed above the sun. The whole detour took over a year longer than a direct flight would have, but it was the only affordable way there. So what did Ulysses actually find above and below the sun that we'd never measured before? The first surprise: the solar wind blowing from the poles moves faster and steadier than the wind blowing from the sun's equator. Equatorial solar wind is turbulent, gusty, unpredictable. Polar solar wind flows almost twice as fast in a smooth, near-constant stream. That single measurement rewrote models of how the sun sheds material into space. The second surprise was the magnetic field. From Earth, we'd always assumed the sun's poles worked like a bar magnet, simple and orderly. Ulysses found the field above the poles was far messier than expected, and it doesn't stay put. Roughly every 11 years, the sun's entire magnetic field flips. North becomes south, south becomes north. So the honest answer to what's above the sun isn't fixed. It depends which point we're in of an 11-year magnetic cycle. This is the first myth correction. School taught the sun as a static ball. It isn't. Its poles are a moving target, magnetically speaking. Now let's zoom out from the poles to the bigger geometric question. What's above the entire solar system, not just the sun? Picture the ecliptic plane as a flat dinner plate with the sun at the center and the planets embedded in its surface. Above that plate is just space, thinning out into the outer edges of our star's influence. But it's not empty in the way most people assume. The sun's magnetic field and solar wind extend into a vast bubble called the heliosphere. That bubble isn't a perfect sphere. It's stretched, almost teardrop-shaped, as the sun moves through the galaxy. Above and below the ecliptic, that bubble still exists, just thinner, less shielded by the dense equatorial solar wind, which means the region above the sun's poles is, in some ways, more exposed to interstellar space than the region around its equator. Voyager 1 and 2 confirmed this when they crossed the heliosphere's edge, both roughly within the ecliptic, not above it. We still don't have direct measurements of that boundary from directly above the sun's pole. No mission has gone far enough north to check. That's an honest gap in human knowledge, not a mystery dressed up for drama, just a place we haven't sent instruments yet. Let's come back down, literally, to what's directly below the sun in that same framework. Ulysses also flew under the sun's south pole on the return leg of its long looping orbit. What it found below matched what it found above almost exactly. fast, steady solar wind, a tangled, shifting magnetic field. That symmetry told scientists something important. The sun's strange polar behavior isn't a one-sided fluke. It's how the whole star works. Which brings us to the second myth correction. People assume the sun is one uniform sphere of fire in every direction. It isn't. Its poles behave differently from its equator. Cooler in some measurements, magnetically wilder, aerodynamically calmer in terms of wind. The sun is not a ball. It's a layered, rotating, differentiated system, and direction matters to how it behaves. That alone is worth sitting with. Something we've stared at every day of human history still has sides we barely understand. Now, the more ambitious question the diagram never prepares you for: what's above the sun on a much bigger scale? Zoom out past the heliosphere entirely, and above the sun starts to mean something different. Above the galaxy's disk. The Milky Way is also a flat disk, much like the solar system, just built from hundreds of billions of stars instead of 8 planets. Our sun sits inside that disk too, roughly 2/3 of the way out from the galactic center. So above the sun, in galactic terms, is simply less of the Milky Way's stars and a clearer view out into deep space. That's actually why astronomers prize looking north or south of the galactic plane. Less dust in the way, cleaner data. Looking along the galactic disk, dust and gas block the view like fog on a motorway. Looking above or below it, the fog clears. So, in a strange way, the direction above and below the sun is where the universe becomes easiest to actually see. That's not a coincidence dressed up as poetry. It's orbital mechanics and interstellar dust distribution plainly explained. Let's go back to something people genuinely search for and rarely get answered clearly. Does above the sun mean anything for us on Earth? Earth's axis is tilted about 23 degrees relative to the ecliptic plane. That tilt is why we have seasons at all. So Earth itself is never perfectly level with the sun's equator. We're always slightly above or below its equatorial plane, depending on the season. In practice, that shift is small, just a few degrees, but it's enough to change how solar wind and radiation reach us across the year. This is why solar storms don't hit Earth with identical force every time. Our position relative to the sun's equator shifts constantly. So even Earth's own relationship to above and below the sun isn't fixed. It's a slow yearly wobble, not a static line. Now, here's where the story gets a genuinely new chapter. In 2018, a mission launched that could finally get close enough to test all of this directly. The Parker Solar Probe wasn't built to go over the poles. It was built to go closer to the sun than anything ever had. It flies through the sun's outer atmosphere, the corona, at speeds no spacecraft had reached before. It carries a heat shield designed to face temperatures over 2,500 degrees Fahrenheit, while the instruments behind it stay near room temperature. Its data has already confirmed something Ulysses only hinted at. The fast, smooth solar wind really does originate from the poles, from structures called coronal holes. Coronal holes are literally cooler, less dense regions where the magnetic field opens straight out into space, instead of looping back down. They sit at the poles most often. That's why the fastest material leaving the sun tends to leave from directly above and below it. So, the honest, complete answer: above and below the sun is where its atmosphere breathes out the fastest and cleanest. It's also where its magnetic field is least predictable, flipping polarity every 11 years in a process we still can't fully model. It's a region almost no spacecraft has visited, sitting outside the flat highway every mission is built to travel along. And zoomed out far enough, it's the clearest direction we have for looking straight out of our own galaxy. None of that was in the flat diagram, not because scientists hid it, but because a flat page can't hold a three-dimensional star. This is the pattern worth noticing. It isn't that school lied to you outright. It's that convenience quietly replaced accuracy. A flat drawing is easier to print in a textbook margin. A three-dimensional, magnetically flipping, wind-streaming star is harder to fit on a page. So, the diagram won, and an entire generation grew up picturing a sun with only a left and a right, and never an up. Only one spacecraft has ever corrected that in person. Ulysses finished its mission in 2009 after 19 years in flight. No replacement mission has been built to go back. The poles of our own star remain, quite literally, the least visited place in the solar system. That's an odd fact to sit with. We've mapped Pluto's surface in detail. We've landed on a comet, but we've barely glimpsed the top of our own sun. The European Space Agency's solar orbiter is now edging further out of the ecliptic than any mission since Ulysses, gradually tilting its orbit. By the late 2020s, it should reach an inclination steep enough to photograph the sun's poles directly for the first time. For the first time in history, we may get an actual photograph of what's above the sun, not a model, not an inference, an image. Until then, the honest answer stays layered. Above and below the sun is a region of faster wind, wilder magnetism, and a flipping compass. It's a direction almost nothing built by us has ever traveled, and it's the clearest window we have out of our own galaxy's crowded disk. Not a line on a page, a place, one we are only just beginning to actually visit. So next time you see that flat classroom diagram, remember it was never wrong about the planets. It was just silent about everything above them. That silence is exactly the kind of gap this channel exists to close, one corrected assumption at a time. If this changed how you picture the sun, subscribe to Space and Beyond. We'll keep fixing the diagrams nobody questioned. So let's finish the picture properly, because the sun's north and south aren't just directions. They're a magnetic argument the sun has with itself every 11 years. At the poles, the sun's magnetic field is almost perfectly organized, running in clean, open lines straight out into space. At the equator, it's chaos, tangled loops, sunspots, flares. The calm parts of the sun are the ones we almost never photograph. That's the irony. The most photogenic sun is the messy equatorial sun. The poles, the quiet ones, barely make it into any textbook image at all. Solar Orbiter, launched in 2020, was built specifically to fix this blind spot, tilting its orbit to actually look down on the pole. In 2025, it sent back the first clear images of the sun's south pole. Humanity had never seen it face-on before. Not once. Every photo of the sun before that came from roughly the same angle, the plane where the planets sit. We'd been staring at its equator our whole existence. Imagine studying a person's face only from directly below their chin for 400 years, then finally seeing the top of their head. That's roughly the scale of the correction. Not a new discovery about some distant object, a blind spot about the nearest star we have. And what the pole showed wasn't calm at all near solar maximum. It was a mess of mixed magnetic polarity, north and south tangled together. That mess is exactly what happens right before the sun's magnetic field flips entirely, swapping north for south across the whole star. It happens every 11 years, quietly, without warning lights or headlines, and Earth sits through every single one of them. So the next time someone shows you a flat diagram of the sun as a plain circle, ask them where the poles went. Most diagrams simply erase them. The sun was never the simple yellow ball we were handed as children. It has a top, a bottom, and a temper we only just learned to see.